In this module, we will study ordinary least squares regression for two variables. The contents of this module, firstly, are why use a method, what is the need to come up with any method such as the OLS. Secondly, we will study the OLS methodology, that is, how do you get the ordinary least squares coefficients for a regression. Thirdly, we will talk about the properties of OLS estimators which make them particularly useful. Fourth, we will talk about the coefficient of determination or the goodness of fit, which is R square. And fifth, we will study the coefficient of correlation R. To start with, why do we need a method of regression? So for example, if we are given a scatter of plots between x and y and we want to fit a line which best fits these points, then we can construct the points in several ways. For example, we can construct a relatively flat line like this one or a relatively steep line like this one. Now there are two issues with it. Firstly, if two different people construct the same line, they might construct different lines. Secondly, if the same person constructs this line at two different intervals in time, he might end up constructing two different lines. Hence, we must have a methodology which will ensure that every time or every person who constructs this line comes up with the same regression line. One of those methods is the ordinary least squares method. Now the thinking behind this ordinary least squares method is that since we would like to get the best estimate of y for a given x, hence we should ensure that our predicted y is as close to the real y as possible. That is, EI, which is the difference between the predicted y and the actual y, is minimized. Hence we want to plot a line that minimizes these EIs. Since all the EIs cannot be 0 at the same time, let us assume that we are trying to minimize the sum of EIs. However, there is a problem with this methodology. Since some of the EIs are positive, that is actual y is greater than predicted y, and some of the EIs are negative, that is actual y is less than predicted y, in which case they balance out each other and we can construct several different lines such that the summation of EI equal to 0. Hence, if we use this methodology, we will not be able to come up with one single line. Hence, we have two major options before us. Firstly, we can minimize the sum of squares of EIs. Since we are squaring the EIs, hence all EIs become positive, and we then try to minimize the sum of EI squares. Or another methodology is to minimize the sum of the absolute value of EI. In both cases, what we are doing is we are getting rid of the sign of EI, because it does not matter to us whether the EI is less or greater than 0. What matters to us is that EI should be minimum. However, mostly we choose the first methodology, that is minimizing the sum of squares of EIs, because it is easier to carry out further mathematical treatment on this value. We now look at how do we calculate the coefficients using the ordinary least squares method. So the ordinary least squares method goes like this. Firstly, we know that EI, or the error term, equals to the actual y minus the predicted y. However, the predicted y, as we know from regression analysis, is equal to alpha plus beta xi, whereas alpha is the intercept term and beta is the slope term. Hence, we can write EI equals to yi, which is the actual y, minus alpha plus beta xi, which is the predicted value of y. Since we want to minimize summation of EI square when we are doing OLS, hence we will try to minimize summation of yi minus alpha minus beta xi whole square. Our objective is to minimize summation of EI square. We are already given yi's and xi's, and hence the only variables here are actually alpha and beta. Hence, for those of you familiar with differential calculus, you would know that the first order conditions are that the partial differential of summation EI square by alpha equals 0, and the partial derivative of summation EI square with respect to beta is also equal to 0. Now here is how these equations are solved mathematically. Let us pick up one of them. Let us pick up summation EI square by alpha. It is given to be equal to 2 into summation yi minus alpha minus beta xi into minus 1 equal to 0. This is the result from the partial differential. We multiply both sides by -2 and we get that summation of yi minus n times alpha minus beta times alpha xi equal to 0. After which we finally get the equation that summation yi equal to n times alpha plus beta times summation xi. Similarly, we get another equation when we do the partial differential with respect to beta. These two equations are known as the normal equations. While the mathematics behind the derivation of these normal equations might not always be relevant, it is nonetheless a good thing to know how we came up with these normal equations. Hence, we are given two normal equations in two unknowns, the two unknowns being alpha and beta. You can solve these two equations in two unknowns using several methods, the easiest of which I think is the Cramer's rule. And finally, you come up with two equations. One gives the value of alpha and one gives the value of beta. The value of alpha is equal to mu y minus beta times mu x, where mu y is the mean value of y. Similarly, beta equal to summation xi yi divided by summation of xi square. However, these are small x and small y, which represent the deviation of the x from its mean value. You will see further in this module that it is often much easier to write coefficients or other variables in terms of their deviations rather than their absolute values. Sample regression function or the sample regression line obtained by the OLS passes through the mean values of x and y. Hence, no matter what the x and y are given, it will always pass through the mean values. All these properties can be mathematically derived from the derivation of the normal equations. For example, if we talk about this first property, then you could refer back to this equation and divide both sides by n. So the equation you will get will be that mean value of y equal to alpha plus beta times mean value of x, which basically means that these 2 points, mean value of y and mean value of x, lie on the sample regression function. Similarly, another property is that the mean value of ei's in this case is 0, that is summation of ei equals 0. As we had previously said, this is not the only line which has this property, but this is one of those lines which has this property. Thirdly, xi and ei are uncorrelated, that is summation of xi into ei equals 0. This is an important property when we will study hypothesis testing. However, we should also note that in case xi's are fixed, that is xi's are given to us, which is mostly the case, then this property is automatically fulfilled. Also, a corollary of this property is that summation of xi ei, where we talk about small x or the deviation of x from its mean, is also equal to 0. The fourth property is that the predicted y and the ei are also uncorrelated, that is summation of yi hat into ei equals 0. The derivation of this property is given as a subnote on this slide. Now we come to the coefficient of determination or the R square. It is a measure of goodness of fit, that is, it is a measure of how well our line fits our numbers. It measures what percentage of deviation of y from its mean mu y is explained by the deviation of x from its mean mu x. The mathematical derivation of the coefficient of determination is as follows. We know that yi equals yi hat plus ei. Now subtract mu y or the mean of y from both sides. We also know that yi equals yi hat plus ei. Now squaring both sides, and after going through a number of mathematical manipulations, we finally arrive at the fact that the total sum of squares, which is represented by summation yi square, equals the estimated sum of squares, which is explained because of the deviation in xi, and the residual sum of squares, which is the unexplained component. Now R square is equal to, as we said, the explained component by the total component, and hence is equal to 1 minus the unexplained component RSS by the total component, which is 2 TSS. Coefficient of determination has certain very good properties. Firstly, it is a non-negative quantity, because by saying that it is r square, it is obviously that a squared value cannot be negative. Also because it is equal to 1 minus summation ei square by y summation yi square, which is equal to beta summation xi square by summation yi square. And since both numerator and denominator are positive values, hence the r square is also a non-negative quantity. Moreover, since it is the division of a part, which is the ESS, divided by the whole, which is the TSS, hence it cannot be greater than 1. So we know that r square will have to lie between 0 and 1. The coefficient of correlation, or r, which you would have come across even in other settings, can be found out using the coefficient of determination also. As you already know, it is a measure of strength of linear relationship between two variables. However, it is also the square root of the coefficient of determination. So the higher the coefficient of determination, the higher is the coefficient of correlation. However, the subtle difference being that r square, being a square, can be only a positive value. However, r can be both positive and negative. If the relationship between the two variables is negative, then r will also tend to be negative. However, looking at r square, we might not be able to come up with what the sign of r is. So the sign of r is always the same as the slope coefficient. If the slope coefficient is negative, it means there is a negative relationship between the two variables, and hence r should also be negative. Hence we found out another way of deriving r from linear regression. This brings to an end our study of linear regression. After this, we will talk about hypothesis testing on OLS estimators and multivariate regression.